Let us recall what we have did into the previous lecture. So in the previous lecture, we have defined very important concept that is called open sphere. To define open sphere, you require one metric space X and a point in that metric space with the metric D. Then S R of X0, where your R is greater than 0, is a positive number, which define as set of all points in X such that distance between X and X0 is less than R. So this is the definition of open sphere that we have discussed in previous lecture. Also, we have seen lots of examples of open spheres with the same space, with the same set of points. The open spheres will be different if you change your metric on that set. The next definition that we have defined, it is an open set. So what is open set? For that also you required one metric space X comma D, and G will be a subset of X. If you want to say that this set G is an open set in X, if for every point in G, so for every point in G, there exists some neighborhood. So I can say there exists some R greater than 0 such that SR of X is a subset of G. So this is the definition of open set, and using this definition we have solved certain examples, or we have seen some examples of open set with a different metric. Let us discuss today some important theorems which based on open set. In that, the first theorem you will have, it says that let X be a metric space then prove that the empty set phi and the full set X are open in X. That means the empty set and the set X, they are always open. This is the statement. Let me give you a proof for this statement. You should know what will be the definition of the open set. The open set is defined like this. If you want to prove that phi is an open set, then you have to prove that for every point of phi there exists some neighborhood which entirely inside that set. Or I can say that it is equivalent to prove that each point in phi is a center of open sphere containing phi. But the phi does not contain any point. Therefore, I can say that for every point of phi, there exists one neighborhood of that point which contain in phi. So that's why phi is an open set. Let me write the same concept here. what we have to show is phi is an open set. It is equivalent to prove that each point in phi is the center of open sphere contained in phi. So each point of phi, but phi does not contain any point, but phi does not contain any point. So hence what we can say, therefore phi is an open subset of X, because for every point of phi we have this same property. Even though for X, now next we need to prove that is X is an open set. So by definition, what you have to prove, that for every point X in X, there exists a neighborhood which is lies entirely in X. So according to that definition, what we can say about X? Where is the sphere come from? A sphere is always a subset of X, because we are taking all the points which are from X. So the sphere is always a subset of X, whatever the point you will take into X. So as per that argument, we can say that X is an open set. So we can say that every open sphere with center on each of its point contained in X. So every point open sphere is a center of some center, and for each point it contained in X. So therefore we can say that X is an open set. Therefore X is an open set. So ultimately what we have proved here is the set phi and the subset, a full set, is always an open set. Now in the previous lecture we have noted that the closed interval 0, 1, open 1 is not open in R, that we have proved in the previous lecture. Okay, this is open interval. So it is closed open 1 is not an open set in R. But if we consider X, our X as this set, so whatever the subset or whatever the neighborhood I am drawing, which is always a subset of X. So in that sense, or in that case, this X is an open set. Due to the previous result, the full set is always an open set. Okay. So the same metric, whatever the metric we are defining is this usual metric. But as this closed interval or this closed 0 open 1 is not open as a subset of R, but it is an open as a subset of itself. That is the conclusion that we can make from this. Next result that we have is every open sphere is an open set. So I am taking, let X comma D be a metric space. Then prove that every open sphere in X is an open set in X. So how to prove this? So what is the situation? You have a one set. This is your set X. There is one point. Let's say that point is X0 and there is a neighborhood, or I can say a sphere of that point. And we have to prove that this sphere or this neighborhood of X0 is an always, whatever the metric is there, it's always an open set. That means what I need to prove, if I pick any point in this neighborhood, let's say that point is Y, for any point in this neighborhood which always have one open sphere of that Y which contains entirely in that set. That is our objective is to prove. So for that I am starting with, let SR of X0 be an open sphere in X. So I am taking one open sphere in X. What I want to prove, for every point in this set, in this open sphere, will have one open sphere which contains entirely in this sphere. So take any point X in the SR of X. Now I want to find out one neighborhood of this X. This is denoted, I have denoted with the red circle here. So this will gives you, since this point is in this sphere, the distance between X and X0 is always less than R. That is the first thing we can observe. That is, distance between this point and this point is always less than this radius. Now can anybody tell me what should be the radius of this red sphere? What should be the radius I can choose? Because the question is to find out that sphere, because as per the definition it says that there exists some R. So I need to calculate what is that R is. So can someone tell me what should be that this? So let me draw that figure here in large scale. So if you have, this is your X and this is your X0 that we have taken. If you have, this is the neighborhood of this point, and I have taken one point x which is inside this set, and we have observed that the distance between this x and x0 is always less than r, but this distance is r that we have here. So I want to find out now neighborhood of this x. So I can take that radius. So I need to find out what should be that value of r. So here I need to take some radius r1. So can somebody suggest me what should be the radius I can choose? So it is
Norm of r minus r1.
r minus r1 is we need to define. R1 we need to define. So what should be this radius that I am talking about? What is the value of this quantity? So it is always this portion will not go outside this white line. It's easy from visualize from this figure.
So you can subtract dxx naught from r.
Yeah, so
and
it is
divide it by 2.
r minus d of x minus x0. x0. So this is the distance that is we are talking about. So let me draw it with the yellow line. So this distance we need, which is r1 we have said. So it is total distance is r, and you have to subtract this distance from that. That is d of x minus x0. So you will get this distance. So that is this. So if you draw an open sphere of this x with this radius, now we need to prove that sphere. So what is I want to prove? So what we need to prove to show that SR of R1 of x, which is a subset of SR of x0. This is our objective. Now, this we need to prove, because this sphere which we have here drawn, it is SR1 of x. And you have to prove that this SR1 of x is a subset of SR of x0. So whenever you want to prove that this will be a subset of this one, you have to take one point here and you have to show that that point will be in this set. So I'll take any y, it is in this SR1 of x. I have to show that this y is in this. If y is in this, therefore we can say that distance between x and y will be less than r1. Now I want to prove that the distance between x0 and y will be less than r. So I will start with distance between y and x0. I want to show that this is less than r. But by triangle inequality, we can say that this is distance between y and x plus x and x0. So we can write down this is by triangle inequality. But the distance between x and y due to this, let's say this is 1, this is less than r1 plus d of x0. This is due to 1. But what is r1? Value of r1 we have taken. The value of r1 is r minus d of x minus x0. That is, we can say it is star. So therefore what we can say is d of y x0 is less than or equal to R1, the value of R1 is this. So that we will substitute R minus d of x0 plus d of x0 is already there. This is due to star. See, this is the first thing. R1 is there, so plus d x0 is there. So this will get cancelled. So hence we have d of y x0 is less than r. This is not less than or equal to, this is strictly less than. Why? Because here we have strictly less than. So that's why it is strictly less than r. So hence y is a subset of s. Sorry, y is belongs to s r of x0. So hence we can say that s r1 of x is a subset of s r of x0. So we can say that s r of x0 is an open set, which completes the proof of that every open sphere is an open subset of R. Let's do the next example or next theorem. Let X be a metric space a subset G of X is an open set if and only if G is a union of open spheres. What does it mean of this statement? So it says that, let's say the function or some set is G is there. This is the set G is there. This is our set G. If this set G is open, then this G is the union of open sphere. What does it mean? Means that in the previous definition, what we have seen in the definition of open sphere or open set, that every point is a center of some open sphere which is entirely in that set. So if you take any point here, so it will be a center of some open sphere. If you take another point, it is also some center of some another sphere. And if you can union of all the spheres, which is totally inside that set, so that forms and union of open sphere. So if G is open, G is a union of open sphere. That is proved. And the conversely, if with union of open sphere, G is a union of open sphere, then it will be an open set. That you need to prove. That we will see how we can prove that. But let us write down first this argument. The argument is, or our assumption is, G is open, and then we have to prove that G is a union of open sphere. So suppose that G is an open set. What do you have to prove to show that G is a union of open spheres? So there will be first one argument. If G is phi, that means suppose that it is a empty set, then it is an union of empty class of open spheres. And secondly, if G is not an empty set, and since G is open, each point is the center of open sphere contained in it. Like I have given the argument, since G is open, every point has some neighborhood which is entirely in that set. And if you take union of all such open sphere, so that means you will cover whole set. If this portion is left, you will have one point there, which also has some neighborhood which is entirely in that set. So that means we can have this G is a union of open sphere. So therefore, the union of all open spheres is in G. And we already proved in the previous statement that no need. So it is the proof, the argument that G is a union of open spheres. So therefore, G is a union of open spheres. Conversely, that is this portion we are doing. Suppose that G is a union of open spheres. What do we need to prove? To show, we have to show that G is an open set. So whenever you have to prove that G, any set is open, you have to prove that every point of this G contains one neighborhood. So I will start with, for any x in G. But as per the argument, it says that it is a union of open sphere. So can I say that if G is an open union of open sphere, that means G can be write as the union of SR1 of X0, where this SR1 or SR of X0, where this SR of X0 is a subset of all the spheres in that set. Whatever this S is a set of all the spheres. And we have, as per this, G is a union of open spheres. So G can be represented in this manner. So that means we can say that X belongs to union of all these open spheres. But if it is in union, therefore we can say that there exists some R1 greater than 0 such that X is belongs to S R1 of X0. Union, if it is in union, it has to be at least one sphere in which that point is lies in that. But this SR1, this is an open sphere because, and we have proved in the previous statement that every open sphere is an open set. So that means this open sphere contains some another sphere which is having a center at X and which is totally inside this open sphere. So by that argument, what we can write is, since SR1 of X0 is an open sphere, therefore there exists SR2 of X such that SR2 of X is a subset of SR1 of X0 and which is already a subset of G. So we can have for every X in G there exists R2, precisely if I say that greater than 0 such that SR2 of X is a subset of G. So that means this G is an open set. So which proves that if G is an open set, it is treated as union of open sphere. Let us discuss a couple of more examples or a couple of more theorems based on open set. This theorem tells you that let X comma D be a metric space, then prove the following. The first one, any union of open sets is an open set. And the second statement says that any finite intersection of open set in X is open set. So it says that any union of open sets is an open set. That means if you have union of open set is an open. And second statement is that says that finite intersection, that means you will have G1, G2 up to Gn, they are open sets, then intersection of this set is also open set. This says that any union, so it is not finite, here it is finite intersection, but in the case of union, you can take arbitrary intersection, whatever the state you want. Infinite intersection also you can take, arbitrary intersection, union also you can take, not intersection. Arbitrary union of open sets is always an open set. That is the first task we will prove for this. So for that I need to consider some class of open sets to prove the first statement. So consider Gi be a class of open subsets of X. What we need to prove? We have to prove that union of this GI, where I is an any arbitrary, it belongs to some arbitrary set, let's say lambda, is an open set. So whenever you have to prove that some set is an open, you have to take any arbitrary point in this set and you have to find out some open neighborhood of that point. That neighborhood or that open sphere has to be like this set. So to prove that, there will be certain cases. The first one, it may possible each of this GI will be empty. In that case, this union will be empty. So that we will write down first. Case 1 is this GIs are empty. For every I. Therefore, G is equal to union of GI, which is also phi. And we already proved that the phi is an open set. We already know that the phi is open set. So I should not write this. And therefore, G is equal to phi is an open set because phi is always an open set. That we have proved earlier. Case number 2. That is, if G is not empty. That means for some GI, it is not empty. So that ultimately nothing to say that G is not empty. If it is not empty, we'll start with for any NG. If it is in X in G, that means what is G? It is this set which we have union of GI. I have not denoted in the previously, no? Yeah, this is the set G we are saying. So it is the union of all this GI. So if it is in union, what we can say, therefore X is belongs to GI for some I. So there exists some I. So this point is also in that. But what is the things you know that this GI, each of this GI is open. Ultimately, in particular, this GI is also open. Therefore, there exists some R greater than 0 such that SR of X, which is subset of GI. But this GI is always a subset of union of GI, which is already we have. This is always true. So therefore, SR of X is a subset of G. So ultimately what we can say is for every X in G, there exists R greater than 0 such that SR of X is a subset of G. So therefore, G is an open set. And what is your G? It is a union of open sets. So we can say that arbitrary union of open set is an open set. Second statement. What was the second statement? The second statement says that finite intersection of open set is an open set. So what do you have to prove? Here we need to prove that intersection from 1 to n, this is the finite intersection, Gi is an open set. So case 1, it may possible this intersection is phi. If this intersection is phi, then we know that if I call it this is as G or G1, no, G1 is not better because G1 is confused with this G1, so it is, let's say, H. So this H is an open set because this is the situation we have. Case number 2. H is not empty. If it is not empty, we can start with for any x in H. But what is H? H is nothing but the intersection of this. So X is an intersection, that means this X will be inside all this Gi. So I can say that therefore X is belongs to Gi for every I running from 1 to n. For every I, this is there. But each of these GIs are open, that we have already is the situation. Since this GI is an open set for every I from 1 to up to n. So since it is an open, there exists some R I greater than 0 such that Sri of X is a subset of Gi for every I running from 1 to up to n. So can I say that now this Sri of X is a subset of H? Can you say that? Yes, anyone? Can we say now Sri of X is a subset of this H? So what is the situation? Let us see that. Okay, let's say this is the set G. This is the set G2. This will be the set G3. So we'll take only three, and this X is in here. This X, it is an intersection of all these three. So that point is lies in all these three. Now for the G1, let's say this is G1, this is G2, and this is G3. For G1, maybe this is the sphere of this X. For G2, maybe we don't know, but it is entirely in this set and it is this sphere. And for G3, we have this is the sphere of G3. Okay, so it may happen that you cannot say that this all this Sri of X is lies inside the intersection. So you have to choose such thing or such a way that radius of this sphere which we required is inside this intersection, that is in H. So anyone can tell me what is that? So you have to choose here some radius. Say, choose this radius as minimum of R1, R2 up to Rn. So whatever the minimum radius out of this case, R1, R2 and R3. And that minimum radius is, so what we get? SR of X is always a subset of SRI of X for every I running from 1 to n. And this will tells you that SR of X is subset of SRI of X, which is a subset of GI for every I running from 1 to n. And since this is true for every I, this SR of X, it is in intersection. So therefore, you can say that for every R in H, sorry, not every R in H, for every X in H, there exists R greater than 0 such that S R of X is a subset of, and therefore H is an open set, which is the intersection of certain intersection of open spheres, sorry, open sets. Now the obvious question one can ask, can somebody ask what should be the obvious question?
Why not infinite intersection?
Yeah. Why not the arbitrary intersection of infinite of open set is an open set? Okay. So probably you have learned about in analysis 1, I think so, it covered this interval In. I will define like this: minus 1 by n to 1 by n for every n belongs to n. Is this an open set with usual metric on R? So we can say that, yeah, because the same argument as given in the previous lecture for open interval 0, 1, the same argument will work here. Okay. So I can say that each In is an open subset of R. Barabar? What will be the intersection of this In? If I running from 1 to infinity I, what is the intersection of all these intervals? You just see the counter thing. For example, if n is 1, I1 is minus 1, 1. I2 is minus 1 by 2, 1 by 2. I3 is minus 1 by 3, 1 by 3. So first it will be this interval 1 to 1. This is the 0 here. Then it is half 1 by 2 to 1 by 2. Then it is 1 by 3 to 1 by 3. Then 1 by 4, 1 by 4. And if you take the intersection of all these intervals, what will be the intersection? Yes? What is intersection? You just
Greater than 0.
yeah, you will just remember the theorem. It is the theorem called Cantor intersection theorem, I think. In that you are dealing with the same concept in analysis 1. So this intersection will be singleton 0. And we already know that, we already proved that singleton 0 or singleton element, in fact we have proved that any finite set as a subset of R is not an open set. Okay, so we note that is not an open set, open subset of R. So that's why the infinite intersection of open set will not be an open set. Okay, so this is the counter example for that statement. Let's discuss another concept. Before that, let me start.